Managing network traffic in Kubernetes is something that's both common and sometimes complex. For example, you might want to control the network flow for security reasons, such as controlling which pods are allowed to talk to each other. Or you might want to manage the safe release of a new application version by splitting and controlling the amount of traffic that gets directed to two different versions of the same app. Other increasingly desired patterns are those associated with managing the cost and latency of network traffic in the cluster. And that's what I'm going to focus on in this video. Cost is something that a lot of companies and teams are concerned about right now. And there are many facets tied to cost management and networking in Kubernetes. But in this video, I'm going to scope it down to load balancer to pod communication and inter-pod communication. And a lot of these high network costs that teams want to curb are typically associated with cross-zone traffic movement. That is, traffic leaving one zone for another. That's the cost side of things. But what about latency? Latency is very specific to the type of application that you are running. For some teams, it could simply be a nice to have, but not as much of a priority as cost optimization. For other teams, low latency between pods is pivotal for the optimal performance of their applications. Natively, Kubernetes has distinct features that support these use cases, but separately. Topology-aware routing is used to increase the likelihood of sending traffic coming from a certain availability zone to a destination in the same zone. By implication, this reduces the costs tied to egress cross-zone traffic. And then you have the service internal traffic policy, which dictates the exclusive use of node local endpoints so that interpod communication is restricted to the underlying node. But there is a constraint. At this point, these two features can't be used together. However, you can still adopt a pattern to address cross-zone traffic costs and low latency requirements by combining Istio with Kubernetes' service internal traffic policy. So what exactly would this look like in an architectural setup? The way you combine Istio's cross-zone traffic control with the service internal traffic policy will largely depend on three things. The first important thing to consider is the role that each microservice plays in your larger system. For example, one service might function as an API gateway for other services and only receives external traffic. Or you might have a microservice that serves both external and internal requests, and another that only receives internal requests from other microservices. The second important thing to consider is the network traffic patterns across your microservices. And this can quickly become very complex, but it's so important to understand how traffic is expected to flow through your system based on the way microservices interact with each other in the different requests. And the third thing that you have to think about is the way that your microservices should be deployed across your cluster's topology. Are all microservices meant to have their replicas spread across all nodes and in all AZs? Are certain microservices supposed to be co-located on the same node as others for better performance? This information is going to inform how you apply the necessary traffic policies for both cost optimization and low latency. In my demonstration, I'll cover these three areas as I work towards combining Istio's destination roles with the Kubernetes service internal traffic policy. My example has three microservices. First, I have a GraphQL microservice that receives external traffic requests and plays the role of a data aggregator or an API gateway of sorts, and it talks to both orders and products, my two other services. The orders microservice can be accessed both through the GraphQL API or it can be communicated with directly. I have two versions of orders, and both are fronted by the same Kubernetes service. They each return a different list of orders. And in addition to that, Orders 2 has an extra endpoint that communicates with products. And finally, I have the products microservice. It doesn't send requests to any other API. All it does is serve internal traffic requests coming from orders and GraphQL. Like orders, there are two different versions of products that each return a different list of products. And in this demonstration, orders plays a key role in serving requests from both GraphQL and directly from the Istio Ingress Gateway. And as I mentioned before, it also sends requests to products. Products just responds to the internal requests that it receives. Both are going to be highly available across different nodes and in separate AZs. Because orders receives external traffic that originates from a highly available load balancer in different zones, I'm going to apply a policy to demonstrate how to control zonal traffic from microservices that fulfill a similar role as orders. And because products just serves internal requests from GraphQL and orders, I'm going to co-locate it with the relevant pods and then apply an internal traffic policy to ensure that it only receives requests that originate from the same node. So we can minimize egress cross-zone traffic costs for external traffic going to orders and reduce low latency and costs associated with the traffic going to products. Now, for production setups, this means we should also have topology spread constraints in place to make sure that we have enough replicas spread across different nodes and AZs. Also, we should have pod affinity rules to make sure that pods that need to communicate with each other are co-located on the same nodes. Finally, I just want to say that this approach that I'm proposing is ideal for environments that already have a service mesh like Istio. That way, this would merely be an extension of what you're already using it for. Otherwise, taking on a whole service mesh only to use a minor aspect of it may cost you in terms of the operational overhead and managing the other components of the mesh. So just make sure to plan accordingly. All right, that's enough talk. Let's take a look at this in action. All right. Let's start by looking at the deployed topology of the microservices and how they're spread across the different nodes and zones. To do that, I've got a script here that's going to get all the pods in the e-commerce namespace from a set of nodes that are specifically running all three e-commerce related microservices. The results will be printed to a text file, but will also appear in the terminal when I run it. I've also specified the AZs where each of these nodes resides. And I'm going to quickly switch to K9S so that you can confirm that the AZs that these nodes are running in aligns with what I've specified in my script. To do that, I'm just going to focus on the last figure in the IP for each of the nodes. So let's take a look at the first one, which has 156 over here, and I've specified this is running in AF South 1B. So I'm going to come to K9S. So this is our first one over here, 156. I'm going to describe that, and as you can see, it's running in AF South 1B. Let's take a look at the next one, 110, and this is running in AF South 1A. I'm going to come back to the terminal. That's this node over here, and as you can see, it's running in AF South 1A. So the last one, which is 119, I'm just going to describe that. And this is running in AF South 1B. If I come back to my script, you can see there 119 I've specified correctly is running in AF South 1B. Now that we've confirmed that, I'm going to switch back to the terminal over here, and I'm going to execute this script. Great. So we can see over here that the first node, which is running in AF South 1B, has GraphQL, orders 1, and products 2. On the second node, which is running in AF South 1A, I have orders 2. And on the third node, which is running in AF South 1B, I have products 1. So we've got a lay of the land at this point. At this point, there are no destination rules or changes to the default traffic policies, and I'm going to quickly confirm that now. As you can see, there are no destination rules in place. And if I switch to services, take a look at the services for each one of my microservices, you'll see that the internal traffic policy is set to cluster for the GraphQL service, which is the default setting. And that's the same for the orders service. The internal traffic policy is set to cluster. And we'll see the same thing for products as well. Let me switch back to the pods view here in K9S and come to Postman. So when I run queries either via GraphQL or directly to the orders API, there will be somewhat of an even spread in the responses that I get back from both orders versions and both products versions. For orders, this is going to be reflected in the list of who the orders are for. So you can see for the last request that I run, we have an order here for Bruce Wayne. And if I scroll down a little bit further, there's an order for Steve Rogers, Tony Stark, so on and so forth. So we have a list of DC and Marvel characters. But the other version of orders is going to return a list of different characters. We'll see James Lake Jr. and Claire Nunez, etc., etc. That's how we'll be able to differentiate between the feedback or the responses from our two different orders versions and to see or track what the distribution of traffic looks like. For products, this will be reflected in the list of products. You can see over here, we've got a product 1A with the name Envoy hoodie. In the other list, this will be Kubernetes t-shirt, so on and so forth. This is just so we can distinguish between the two different versions and see that our traffic is hitting the different replicas. Now, just a reminder, all requests go through the Istio Ingress gateway, and there are 3 endpoints that we are going to be working with. First is the GraphQL API, and this request will aggregate data from orders and products. GraphQL will first reach out to orders, and when that data is resolved, GraphQL will then reach out to the products API with the associated orders ID. And then it will return all that data aggregated. And then we have the orders API. And when we reach out to the orders API directly, I'll be able to get feedback from the 2 different versions, as I mentioned before. Again, you can see here a list of DC and Marvel characters, but this is just for one of the versions, and we'll see that even spread. Before we take a look at this 3rd endpoint, I'm going to run some queries now, just for these first 2 that we've spoken about. And you can see that I'm getting a list of different characters here, James Lake Jr. So just pay attention to the ordered for and the product data and notice the changes. It will be somewhat of an even spread. All right, and if I come to this orders API, it's a little bit clearer here just to see that the list keeps changing back and forth between these 2 orders lists. That means that we have an even spread between our 2 different orders versions, and it's the same for products as well. This will be made a little bit clearer in Kayali. So let me collapse this, and I'm going to say in the last 2 minutes, let's refresh that and hide that. And let's zoom in just a little bit more. Great. So as I mentioned, all requests are going through the Istio Ingress gateway. So let's have a look at the traffic flow over here. For this first request that we were running, or rather this first endpoint that we were sending data to, the traffic goes through the GraphQL service and then gets to the GraphQL replica. And the GraphQL replica, as I mentioned, first communicates with orders. And it's able to communicate with both versions of orders, which is why we see the 2 here. Now in Kayali, this is represented by the exact versions, but to make it easier, I'm just calling them orders 1 and orders 2, although Kayali has specified the tags details for the actual images, which is a much better practice. And I've got orders 2 over there. And when that data gets resolved, that feedback or that response comes back to GraphQL, which then in turn sends a request to products. And for products, there are 2 versions, and GraphQL will essentially get responses from these 2 versions. So that is why we were seeing the different responses that we were getting. We're getting an even spread of responses from these 2 and an even spread of responses from these 2 as well, both orders and products. So next up, I'm going to make a 3rd type of request, still with the orders API, but to a different endpoint, as you can see over here. Previously, I sent a GET request to the orders endpoint, whereas this is orders products. And this is going to return a list of orders along with their associated products. In the previous request, this only returns the product ID associated with a particular order, whereas here we should get full details. So it works similar to the GraphQL aggregator, except in this case, the request to products will originate from orders itself. Also, just remember, one version of orders doesn't support this endpoint. So we'll see somewhat of a 50-50 or an even spread between successes and errors. As you can see, the last one failed. We got a 404 response because we had a request sent to orders 1, which doesn't support this endpoint. So I'm going to run a few of these requests. You can see now we get 200 response, and you can see the product here associated with the particular order. And if I keep running that, you see now we get 404, and it's going to be like this on and on because we have an even distribution between those different replicas. Let's take a look at what this looks like in Kayali. And I'm going to just refresh that and collapse this over here. So remember, traffic goes through the Istio Ingress gateway and then to the Kubernetes orders service. And we have a dead end over here because this is the replica that doesn't support this endpoint. So we had complete failures over there. Whereas this replica, orders 2, if I just click on that just so you can see, this is orders 2 over here. This one does support the endpoint, which is why we have that represented by the success or the green line, and it's able to communicate with the product service, which in turn distributes traffic between the two different replicas of products. So if I come back to Postman, notice that when we get a successful response, on one occasion we have the Kubernetes t-shirt. If I try that again, now we have the Envoy hoodie. So that's just representing the fact that we are communicating with the two different replicas. Now that we've sent requests to all three endpoints, let's have a look at the full request map. Remember, all traffic originates from the Istio Ingress gateway. And then let's look at the first request, which I already discussed, but let's do it in context of our full map over here. Traffic went to the Kubernetes GraphQL service and then the GraphQL replica, which then communicates with orders, both replicas. When that data is resolved, GraphQL then sends another request through to products, and that gets sent to both replicas, gets resolved, and we get the aggregated data as a response. Then we looked at the orders endpoint, and that communicated with both replicas successfully. And remember, we were getting the alternating responses in terms of the two different lists. And then the third endpoint that we hit was orders products. Traffic came to the orders service, and then one of the replicas doesn't support that endpoint, which is why we were getting errors from it. But 50% was successful in being sent to orders 2, represented by this tag, which successfully communicated with the upstream services in products. So if I click on this line over here, you'll see that we were getting a 50-50 success and error response rate, and that confirms that. All right, let me collapse this, and we will start applying some changes to how traffic is distributed. So what I'm going to do now is apply this destination rule to the orders service so that 80% of traffic, regardless of where it's coming from, gets sent to AF South 1A, where orders 2 resides. Let me quickly come back to my terminal where I run this particular script so that we could see the deployed topology for the microservices. And you'll see orders 2 is running on a node in AF South 1A. Let me open up Kayali and head over to the applications. I'm going to collapse this. I'm going to click on orders and then orders 2. And just so you can see that orders 2, remember, is represented by this particular version tag 0.37 alpha. So in terms of what we should expect to see from the responses, we'll see more of the orders list that consists of James Lake Jr., Claire Nunes, Tobias Domzowski, etc. And we'll see less of the DC and Marvel characters, not only with our GraphQL requests, but also the other orders endpoints that we have in Postman. And remember, I'm only using these specific settings in my destination rule to show that the weighted locality distribution is working as expected. To reduce cross-zone traffic, this should be set up in such a way that a majority of the traffic goes to the same zone where it originated from. That's what you should be doing for a production or real-world setup if you do want to reduce the costs associated with egress cross-zone traffic. All right, now I'm going to go ahead and apply this destination rule. You see that that has been created. And now I'm going to test these same endpoints once again in Postman, and let's see the responses we get. We should see more of this list. You can see over there, as I'm hitting send, there's our first appearance of the DC and Marvel characters. But for most of the responses, we're seeing the James Lake Jr. list. And if I come to orders over here, it should be the exact same thing. Less of the DC and Marvel characters. Now, if I come to this third endpoint, we'll actually see a reduced error rate. Before we had a 50% error rate response, but now, because most of the traffic is being sent to the orders version that does support this endpoint, we'll see more successes. There's our first error. There's our second one. But as you can see, there are more successes. So let's take a look at this in Kiali. Go back to the graph. I'm going to collapse that. I'm going to set this to the last, let's make it the last 2 minutes. And then I'll collapse this over here. And let's send a few more requests so that we have a wider or bigger pool of data. I'll make this the last minute, and that's exactly what I want us to see. So you'll notice that now the line over here is yellow, and the reason for that is because, yes, there are errors as represented by the red line over here, but there are more successes. And in fact, if we click on this specific line, you'll notice that the margin of error or the error rate has reduced drastically. It's about 19%. And if you think about what we've done with our destination rule, we said 80% of traffic should be sent to the zone where orders 2 resides. And orders 2, remember, is this particular replica, which does support that endpoint. So even the data that we get and the reduced error rate reflects the traffic changes that have taken place because of the destination rule that is in place. So even though we've seen a change in the orders responses, we're still seeing the same kind of responses from the products versions, which is an even split in the data that we get back. So now I'm going to add an internal traffic policy to the products service. So far, I've demonstrated a scenario where we restrict zonal traffic to orders, but now we also need to meet the additional requirement of low latency for internal traffic that gets sent to products, which is what this internal traffic policy is going to help with. And another positive side effect of the internal traffic policy is that it can also help reduce costs because traffic will be restricted to the node and won't leave for other products endpoints in different AZs. So I'm going to come here and apply this now. If I head over to K9S and then go to services, I should see this update. You can see the internal traffic policy for products is now set to local. Now, before we do any testing, I want to come back to this existing topology deployment for our microservices and get an idea of what will happen with both the destination rules and the internal traffic policy settings in place. Firstly, products 1 is isolated on this particular node in AF South 1B. So we shouldn't expect it to receive any incoming traffic that is destined for the product service because of the internal traffic policy. Products 2, on the other hand, is on this node in AF South 1B with GraphQL and orders 1. So what should we expect to see with regard to our postman requests? I want to quickly come back here, and this time we're only going to be concerned about the orders products endpoint because there's actual communication with the products API, and the GraphQL API or endpoint because that's where we have both orders and products. This one has no communication with products whatsoever, so we're not concerned with it. Let me come back to my terminal. Now remember, the destination rule is sending 80% of all traffic coming from the different zones to AF South 1A, and by implication, orders 2. This time, let's start with the orders products endpoint. When we send a direct request to this particular endpoint, we're going to get 100% error rate. Why is that? Well, when 80% of the traffic comes to orders 2 is going to try to communicate with the product's API so that it can resolve and return this data. However, because of the internal traffic policy, there are no node local endpoints for products, so that traffic will drop. And remember, because we are using this particular endpoint, which orders 1 doesn't even support, that means that 20% of the traffic that comes to orders 1 will fail. So both 80 and 20, our 100%, are going to give us a complete error rate. But what about the traffic that goes through the GraphQL API? So now I'm going to talk about this particular endpoint. Well, we're actually going to see 100% success rate. Why is that? Well, I'm glad you asked. And I think for this, it'll be easier to actually come back to our traffic map. Remember, traffic that comes through the ingress gateway to the GraphQL service comes to the specific GraphQL API. The GraphQL API first communicates with the orders service, which essentially proxies traffic between these two different replicas. And remember, because of our destination rules, 80% of the traffic is going to go to AF South 1A, where orders 2 resides. So we're going to see a lot of the list that consists of James Lake Jr. and co. And when that data is resolved and returned to GraphQL, GraphQL then uses the return data to then communicate with the product's service. And now, because of the internal traffic policy, GraphQL will only be able to communicate with products 2, which is 0.16 alpha. Let me click on this so you can see that. Oh, I might have clicked on the wrong thing there. Let me click on this. There we go. You can see products 2. I'm going to collapse this. And so we will see the same list every time when there's communication between GraphQL and products. And that list is the one that consists of the Envoy hoodie. So we will not see products like Kubernetes t-shirts, Spiffy, sticker, etc. So I'm back in Postman, and now we're going to run some tests, starting off with the GraphQL endpoint. Let me just drop this a little bit so you can see that the query has not changed. We're still trying to aggregate the same type of data. Gonna hit some send requests. And as you can see, we're still getting a majority of our responses with the list that consists of James Lake Jr. and co. However, a constant is the products. We are still seeing Envoy hoodie for every one of our responses. And the reason for that is the destination rule is still dictating 80% of the traffic coming from the different zones to go to zone AF South 1A for orders 2, which is why we're seeing more of James Lake Jr. However, the internal traffic policy is dictating that traffic is only sent to node local endpoints of the product service. So that's why GraphQL is only able to communicate with the product's replica that has this specific list that starts with Envoy hoodie. And as I mentioned, for the orders products endpoint, we're going to get a 100% error rate. Let's take a look at that. Every time I hit the send request, I either get a blank response or I get the 404 error, which I just quickly skipped over there. There we go. Now, the reason we're getting a blank response on most of them is because this is the 80% that is actually going to orders 2. And the reason we see a 200 response rate is because there is successful communication between the Istio ingress gateway and orders 2. However, orders 2 is not able to communicate with products. And so because of the poor error handling in my source code of this particular API, we're not getting anything. But we can confirm this by simply going to K9S. I'm going to go to pods, and I'm going to go to the container for orders 2 so that you can see that internally there's a 503 error. And we'll see this in a much better way when I go back to Kayali. And you can see over here, we're getting a response of 503. But let's look at this in Kayali. We should have a much better view. I'm going to refresh this. I'm going to collapse that. And I'm going to say the last 5 minutes so that we can also see the GraphQL flow. So as you can see, traffic from the Istio ingress gateway to GraphQL, we're seeing green lines because GraphQL is able to successfully communicate with orders. As I said before, and as we saw, 80% of that traffic goes to this particular replica that gets resolved, and then GraphQL is able to communicate with products. But notice that the traffic is only going to products 2, as I mentioned before, products 01.6 alpha. Now, let's look at the flow for the orders products endpoint, where we're just getting nothing but errors. So traffic is successfully getting to the orders service, and from orders service to the orders to replica because it actually supports that endpoint. However, there is a failure every time it tries to communicate with products because there are no node local endpoints. And the reason we're seeing this red line here, just like before, is because orders 1 doesn't even support that endpoint. Now I'm going to click on this here, and let's take a look at some of the traces. And we're seeing a whole lot of red because of all the errors. I'm just going to pick one of these, click on that one, and then scroll down. And let's look at the spans. If I come down here, we'll be able to see the attempted communication from orders 2. And you can see here, sent request to product service. And you can see the specific GET request that was sent to products 1A. And it failed with a response status code of 503, just like we saw in K9S. And the response is that there was no healthy upstream hosts in the upstream cluster. And on it goes. If I open these up as well, we'll see the same details. In this case, it's to the attempted request for products 1B. In this case, products 1C, and on. You'll see we're getting a 503 error. And that brings things full circle. We can see the effects of the policies that we've put in place to control traffic in our environment.